All right, welcome back to Calc 2. This will be part B of Lecture 4. So we just got done talking about the average value, the mean value theorem for integrals, and we've worked an example of what this average value is all about. And so we want to shift gears here slightly and begin just kind of setting up for the second fundamental theorem of calculus. And so to do that, we need to basically describe what we mean by an accumulation function. So previously, we've used, A, B, right, some kind of closed interval, where A and B, the endpoints of the interval, have been, constant values to define the limits of the integration of our definite integral. So to define the limits of our definite integral, right? So we've been writing like things like this, from integral from a to b of f of x dx, right? And so where these are constants. So it is also possible to write integrals like this, from a being a constant up to a variable. Okay, when we do that, we'd have to switch the variable in the integrand, and the dx would be a dt rather. And so here, this is a constant value, but this is a variable. Okay, and when we do that, this is frequently done, and when we do that, the function sort of, we would say big F of x equals, this integral. This would be called an accumulation function. So an accumulation function. And I guess, this is called an accumulation function. I guess the interpretation would be that f accumulates the area from a up to whatever value is plugged in for x. Okay, so let's do an example of this just to kind of get a little comfortable with what this is about. So what if I write f of x equals the integral from 0 up to x of the cosine of t dt. Okay. So we can evaluate this, right? We know that the integral of cosine would be sine, that's the antiderivative. And using the fundamental theorem of calculus, we could figure this out really quickly. Must be sine of x minus sine of 0, which sine of 0 is 0, so this would be just sine of x. Okay. Now, so we can evaluate this at different values of x, right? So f of x equals sine of x. That implies, things like f of 0 would be sine of 0. And f of, pi over 4 would be sine of pi over 4. Okay, and so on. Okay, so that's no problem. Okay. So, kind of based on this example, like one of the things that you might be able to notice is that if I take the derivative of this accumulation function, okay, that's basically taking the derivative of the sine of x, what we just saw. Now sine of x is the same as, this accumulation function, 0 to x cos t dt. which we know that well, skip over this, but we know that the derivative of sine of x is equal to cos x, right? So kind of what's being implied here is this, okay, which is something to note, right? So basically the derivative of this accumulation function cos t dt is just cos x. So, you wouldn't want to just jump to this conclusion, but there is something quite inherently nice here, right? So basically, if this is an accumulation function, then the derivative of the accumulation function is just the integrand evaluated at the upper interval. Okay, that's kind of remarkable. And this result is generalizable as the second fundamental theorem of calculus. Okay, so let's talk that one through. So you kind of probably already know what this is going to say, but let's say it anyways. If f is continuous on an open interval containing a, then for every x in the interval, the derivative of the accumulation function from a up to x of f of t dt is equal to f of x. Okay, so the derivative of the accumulation of a function of f from a up to x is just f of x. Okay, so this this can be proven. It's not a bad proof at all, actually. Let's do it. So start by defining this accumulation function. F of x equals the integral from a up to x of f of t dt, right? So that's the starting point. And then we're going to differentiate this thing, right? We're going to use the definition of the derivative. So by definition of the derivative, f prime of x would be equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x, all divided by delta x, right? So this is just the definition of the derivative back from Calculus 1. Now, what do we have to do next usually, right? Well, usually we have to actually plug in the function. So for those of you who did not ever get comfortable with the definition of the derivative, this is going to probably make you bonkers. But it's not meant to be tricky. It's actually pretty straightforward. So f is an accumulation function, right? It's this. So we got to plug that in. Now, what's the variable here? Well, x plus delta x needs to go up in the limit of integration, your upper limit, right? So this would be the integral from a up to x plus delta x of f of t dt minus the integral from a up to x of f of t dt. Okay. No problem. And what we're going to do next here is we're going to, we have this nice theorem. You may recall it says the following. I'll kind of do it off to the side here. Basically says that the integral from a to b of f is equal to negative the integral from b to a of f, right? So if I flip those limits, upper and lower limit, if I flip them, then the integral becomes negative. Okay, so we're going to use that here. So the first one is going to stay the same, x plus delta x f of t dt. But what we're going to do is we're going to add this now, and we're going to flip this from x up to a. Again, this is something we saw earlier on in the course, I think like maybe a couple lectures back already, not too many. That's not too old. Okay, and so that's nice, because then what we can do is we can kind of piece these two together. And instead of having two separate integrals, it'll be one integral from x all the way up to x plus delta x. Right? Remember, a is between x and x plus delta x. So that's going to be the limit as, or sorry, the integral from x up to x plus delta x of f of t dt. Okay. All right. Then hopping over to the next page. And so from the mean value theorem, right, so we have to pull out the mean value theorem. We know from the mean value theorem, there exists a c in the interval x up to x plus delta x such that this previous thing here is equal to f of c times delta x. Right, so this guy here would be equal to, such that we'll just write it x to x plus delta x, f of t dt would be equal to f of c times delta x, right? So that's kind of what we saw with the mean value theorem. Now here, I think with the mean value theorem this is mean value theorem for integrals. What we kind of wrote it differently in the theorem. We had like a b minus a here, but notice if this is your b and this is your a, then x plus delta x minus x is just delta x. So we're kind of just writing it in a slightly different way, but this is, again, just the mean value theorem for integrals. Okay, so we have that. So there exists some c in this range. Now, here's the tricky part. Because x is less than or equal to c, which is less than or equal to x plus delta x, it follows, right? So because this is true, it follows that as delta x goes to 0, okay, as delta x goes to 0, what happens to c? Well, c gets closer and closer to x, right? So if the width of this interval is decreasing because delta x is going to 0, then c is getting closer and closer to the value of x. Okay, so hopefully that, like if the interval shrinks down, then the lower bound of any number in there is going to get closer and closer to x, right? Especially any fixed value, right, would eventually get closer and closer to x. Okay, and so if that's the case, then everything kind of falls out of this, right? So f prime of c will be equal to the limit as delta x goes to 0 of 1 over delta x times f of c times delta x. Okay. And that's going to imply, of course, that f prime of c is equal to the limit as delta x goes to 0 of f of c. Sorry, oops, off the page again, darn it. Right, so these delta x's just cancel out. And so what happens is what we just said, right? As delta x goes to 0, f of c goes to f of x. C is going to be closer and closer to x as delta x gets smaller. So this would be f of x. Okay, now remember, that's what we were trying to show, right? What we were trying to show was that the derivative of the integral from a up to x of f of t dt is equal to f of x. Right, so that's what we got to. All right, so kind of a tricky little theorem. Obviously, there's a lot of moves in that theorem, actually. Then some of this stuff here, it can be a little bit cumbersome, but hopefully, you followed along at least somewhat. And if not, pause the video, go back, and take it step by step. Let's do an example using the fundamental theorem of calculus. This will be the fundamental theorem of calculus. This will be a little bit of a little bit contrived, but that's okay. We'll see what happens. So evaluate the derivative of 0 up to x accumulation function t squared plus 1. Okay, so all we have to know here is that the square root of t squared plus 1 is continuous on the entire real line. There's no breaks, no gaps, no asymptotes, no weirdness. So, and you can see that, right? Because t, whatever you plug in a real number for t, you get a positive value out, and so the square root of a positive value is always defined, no problem. And basically, this, because it's continuous, we can just, basically like use the second fundamental theorem to see that this is just x squared plus 1. Right, that's that derivative. So this is, again, a little bit of a contrived example, but just kind of to show you that, the thing to check here is to make sure that the function is continuous everywhere, right? Because otherwise you can't necessarily do this. But if it is continuous, then the derivative of the accumulation function is really just grab the upper bound, plug it in, done. So the second fundamental theorem of calculus can be, so this is, again, a little bit of a contrived example, but it can be useful. It can be used to help find derivatives also. And that's a little bit less straightforward. So let's talk through this example, which I think is probably where we'll end it, but this is kind of a more complicated example. So say we want to find the derivative of f of x equals the integral from the fixed value pi over 2 up to x cubed. Okay, and then the integrand is cos t dt. Okay, so this is an accumulation function. The upper limit just happens to be a cubed value. Okay, so what you can do is you can kind of think of this as a composite function, right? So you've got the outside function, which is this integral part, and then you got the inside part, which is the x cubed, right? That's a function itself. So we're going to approach this kind of from a chain rule standpoint. So let's let u equal x cubed. Okay, so then the derivative of f prime of x would be equal to the derivative of f with respect to u times the derivative of u with respect to x, right? That's just like the chain rule, right? So writing that a slightly different way, it'd be d du of f times du dx. Okay. Okay, now what is what is f? Let's plug it in here. So this would be d du of the integral from pi over 2 up to u of cos t dt. Okay, so again, just kind of plugging in the u for the x cubed here. Now, this part here, cosine is continuous on the entire real number line, so we don't have to worry about that. We can just use the second fundamental theorem here and get that piece of, oh, sorry, I do need the du dx here. Let's not forget about that. But this part, this first derivative can be calculated really quickly, right? This is just cosine of u. Okay, and so then it's cosine of u times d dx of x cubed. So what do you get? You get cosine of u times 3x squared. And then the cosine of u is really cosine of x cubed times 3x squared. And so I guess best way to write that would be 3x squared times cosine of x cubed. Okay, so it looks like that. Okay, so this would be the derivative here of this kind of messy accumulation function. Now, in this example, actually, the integrand is pretty easily calculated. So we could kind of do this a different way to verify the results. So let's do that. So f of x equals the integral from pi over 2 up to x cubed of cos t dt. So let's just evaluate this integral here and then differentiate that directly. So that would be the integral would be sine t, and that's pi over 2 up to x cubed, and so we can just plug those in. Sine of x cubed minus sine of pi over 2. And so that would be sine of x cubed minus 1. Okay, so that's what f of x is. F of x can alternatively be written as such. Right? You can write it like this, right? If you wanted to ditch the integral. And so if we differentiate this, right? Do we get the same answer as before? I sure hope so. Let's see. F prime of x would be d dx of sine of x cubed minus 1. Okay, this is a simple chain rule derivative. So you would differentiate the outside first, so the sine of u would be cosine of u, and I'm just going to leave the x cubed in there. And then to differentiate the inside would be 3x squared, and then minus 0. And so that is the same answer, isn't it? 3x squared times cos x cubed. All right, so that's going to be the same answer as what we had on the previous page. Okay, very good. So that's a nice application of the second fundamental theorem of calculus. Okay, and so I think we'll end this lecture there. So now that we have the second fundamental the fundamental theorem of calculus, fundamental theorems of calculus, we are going to shift our attention to, we're going to go full on integration techniques for the next at least couple of lectures. I'd say 3 or 4 if I had to guess. Maybe half of the remainder of the class actually, but we might have some breaks in between. But what we're going to be focused on next is how do we integrate. We want to learn how to integrate as many functions as possible. And so that's what's coming next. And I think the next lecture will be integration by substitution, which is by far one of the most useful methods that we'll have. So we will see you then. We'll see you then.